That expression there, I'll just write it here, is Q0 over 4 pi epsilon, and then 1 over R, not R squared, 1 over R. And that's for the electrostatic potential energy between two charges. So if you have a charge here and a charge here, and there's some distance between them R, then the electrostatic energy, potential energy between these two charges is given by this expression. And if you have a group of charges, then you sum algebraically. And remember, it's the electrostatic potential energy filled by the test charge Q naught. Okay, so that's what the is. And then after that, we defined the electric potential. This is the electrostatic potential energy. This is the electric potential, which is defined as the electrostatic potential energy divided by some test charge Q naught. And if you do that, you get simply Q over 4 pi epsilon 1 over R. Okay? So that's what the potential energy and the electric potential, electrostatic potential energy and the electric potential. These are the definitions that, so they're very similar. Remember here, what you're doing, you're taking the electrostatic potential energy per unit charge. Okay, so this is assuming this Q naught is a very small test charge that we had talked about before, and you just want us to look at what is the potential energy per unit charge. Okay, so joule per coulomb. Now, later, maybe later today or next class, we will talk about the electrostatic potential due to any charge, any continuous charge distribution, and then we have again to resort back to integration, and we'll talk about that later on. Excuse me. That's not allowed. Mobiles must be put away. I said this a million times. The only time I allow you to hold your mobile if you wanted to take an image or a click of what we are writing about. But it's not good, and it's insulting when somebody is talking and you're a text message. That's not good. Please. All right, so let's continue. I just wanted to, in this class, I wanted to take a few examples, sort of application to these two equations or two expressions describing the electrostatic potential energy and the electric potential, just to make sure that we understand the difference between them and how we calculate them and the physical difference between the two physical quantities. So let's start with the first question, where we have a point charge Q1 is equal to 4 nanocoulombs placed at the origin. Did we solve this? Yeah, we did. Okay, so let me just go to the next question. Actually, I don't want to look at that. I want to look at this question here. This question says that an electric dipole, which is, we know what an electric dipole is. It's two charges. They have the same magnitude but opposite signs, and they're separated by some distance. In this case, the charge of the magnitude of the charge of the dipole is 12 nanocoulombs. So that makes one of them is negative and the other one is positive. And they are 10 centimeters apart. So the distance between them is 10 centimeters apart. And he wants you to calculate the electric potential, so V. He wants you to calculate V at points A, B, and C. I'll do 2, and then I leave 1 for you to practice. So V, which is defined as Q over 4 pi epsilon divided by R, which is regular. But I want to calculate the electric potential at a point due to two charges. So let me take, I'll take point B and I'll take point C, and I'll leave 8 for you there. So if I take the potential, the electric potential at point B, it will be the electric potential due to the positive charge plus the electric potential due to the negative charge. Okay? That's what by definition, right? Because they have to sum both of them. And the electric potential is defined by that. Remember, the magnitude is the same. So that means what? That means Q over 4 pi epsilon. And then for the, let me just choose this to be the positive charge and this to be the negative charge. Okay, he did not specify which one is which, so I just picked this. So the positive charge at point B will be located at 1 over 4. I'll just keep it in centimeter. Or if you want, I can put 0.04 meter. And then minus 1 over 0.14. Because remember, this is 10 centimeters. So plus 4, that's 14 centimeters. That's the answer. Okay? So Q is given, K is given, everything is given. That's very, very simple. And what makes this very simple, because it's algebraic sum, the only thing that we have to worry about is the negative here, in this case, because of the negative charge. Okay? So that's at point B. If I take the electric potential at point C, so V at point C, again, it will be V due to the plus, or due to the positive charge, and V due to the negative charge.
0.
Okay? You think it's 0?
Yes.
We'll see. Okay? So what does that mean? That means, why do you say it's 0?
The distance between the positive charge and the C is the same between the distance between the negative charge and the...
Okay. All right. So let's see. That's absolutely correct. Okay. So a Q over 4 pi epsilon, and then I have the distance, which is 0.13, and I'm going to pull the Q out, minus 0.13, which is absolutely what she said is correct. Is equal to 0. Okay? So what does this mean? Just like what we did before, there are points in space near charges. There exists a point in space where the potential, the electric potential is 0. This has, of course, huge implications when we do some of the applications. But there are some points in space where we can get 0 potential. Okay? So I leave the second or the third one. He wants you to find it at C. We did that. See, so at A, you can do that very easily using the now you know how. Okay? Okay, this is the question that I sort of started with last time, or I just gave you some ideas about it last time, and then we'll So, what does this question say? It said that it wants you to find the work done or required to assemble 4 identical point charges of magnitude Q placed on a square. So let me just draw that here. So I have a square, right? And I want to assemble these charges. Meaning what? Meaning I have these charges laying down somewhere, and I wanted to bring them here. And I want to know the work needed to do that. Okay? The way we do that is by simply doing it in steps. First thing, I bring what I call Q1. Okay? I bring it here. And then I bring, so when in doing so, in bringing the Q1 the first corner, I have to do no work. Right? Because where is the work going to come from? Where will it come from?
From changing the potential.
Work is equal to what?
The change in potential?
Change in this case, potential energy. Now, negative, yeah. And now, remember what we always do. We say, okay, it's something, some constant, 1 over R. Initial minus 1 over R final. Well, actually, 1 over final minus initial. Okay, it is, the negative is now becomes irrelevant because I have to worry about the charges. Okay? So if I start at infinity, so if my actually it's I minus R, that's right, that's what we did last time, right? So if I start from infinity, so start at infinity, meaning what? Meaning the initial will be equal to 0. So that means my work will be equal to simply the minus, right? Will be K, Q, right? And then over R final. So for this charge number 2, so I'll bring it from infinity and I place it here. Then my work will be equal to what? Is equal to K, which is 1 over 4 pi epsilon, and Q, and the distance in this case is what? 8. So that will be the work required. Let's write that down. The work required to bring Q2 from infinity 2 to the second corner. Let's say second to the second corner. Because that's what the question is. The question, remember, the question, he asked me to assemble these. Assemble these, that means bring them together. Right? In what form? In the form of a square. So he wants to put them in the form of a square. Okay. So that will be my first, simply KQ divided by A. That will be my first, this is the amount of energy that I need to bring the first one. Okay, the third one, the second one. So the third one, what is the amount of energy or work I need to do that? To place this third charge right here. The work in this case, it will be what? Because these are the two guys that I have to bring here, right? So it will be this plus this, right? This amount of work is the amount of work done with this guy, right? And then there is another one, the energy to this one, right? So it will be what? It will be K, Q, the Q's are the same. So it's Q1, Q2, Q3, they're all the same. And divided by this distance here. What is this distance here? If this is A, this is A square root of 2. Huh? Okay? So that will be A square root of 2. And then plus this energy, which is K, Q divided by A. Right? I forgot the Q's. There's two because the energy is Q. So this is Q. Q. Guys, wake up. Alright? So this will be, let me call this the work to bring 2 to that corner. This is the work 3 to bring it to that corner. Okay? Now how about 4? This is the fourth one. What is the work required to bring it and put it here? It will be the work with this one, work with this one, and the work with that one. Okay? So the work, now this is the work required to bring Q2. This is QQ, I'm saying Q1, Q2, but they are the same, so I'm just taking on that. From infinity to the second corner. And this is the work done to bring Q3 from infinity to the third corner. Okay. And the one we'll do is the work required to bring Q4 from infinity to the fourth corner. Okay. So this one will be equal to, the work is equal to, again, this one we've calculated that K, Q divided by A plus K, Q divided by A plus K, Q divided by square root of A square root of 2. Okay? And then simply the total work, so therefore, work 4. You should write here, this is the work done required to bring Q2 from infinity to the second corner. This will be the work required to bring Q3 from infinity to the third corner. This will be the work required to bring Q4 from infinity to the fourth corner. So the net work will be equal to this plus this plus this. So I have 1, 2, 3, 4. So that means 4 K, Q divided by A, plus I have 2 of these guys. Right? 2 K, Q divided by A square root of 2. I can take the K, Q divided by A, and then I have plus 4 over the square root of 2. Okay? No, because let's say if I want to assemble them here, this is my square. Okay? And I want to assemble them here. The first one, I'm going to take it from there. That's very far away, right? And then bring it here. So that would be considered infinity. I bring the second one from there and bring it here. Third one, so forth and forth. It's very important application. So this is simply the work needed or required to bring this. It's 5. So if you look, we have 4 plus this is 1 point something, which is so 4 plus 1 point something is 5 point. Okay? Any questions on how to do this? Right?
Doctor?
Yeah.
Isn't it 3Q over A?
3. I have 1 here.
Oh, 1.
Okay. 2, 3, 4. And I have these two guys.
Okay.
Okay? You forgot the first one. Alright? Guys, please. Okay. So the solution is here. Guys, okay, let's look at this problem here. Actually, we'll leave that. Okay, we have 2 point charges. 2 point charges, Q1, Q2, and they are separated by 0.1 meter apart. Point A is midway between the two charges, while point B is located 0.6 away from Q2 and 0.8 from point 3. Taking the potential, now V, to be 0 at infinity, find the potential at points A and B. We've done this. No, we didn't. Right? We want to find the potential similar to the previous question, so I just do one. So this is the arrangement of the charges, and he wants to find the potential at point A and the potential at point B. So the potential at point A, so this is VA, this is point A, so it will be K, I'll leave it out, and then 2.4, I'm going to leave the nanocoulomb, so I'll multiply by 10, this will be 9, right? 1, so it will be that, that's fine. And then the distance, if this is, he told me that this is 10, which one is 0.1 apart, and the two charges, did he tell us? B is located, which one is 6, 0.6, this one, right? Zero, that's 0.
It's a midpoint. That's going to be 0.05.
Yes, because it's midway.
This is 0.05 in the middle?
Yeah.
Okay, so 0.05, thank you. Okay, meter, right? Okay. So this will be 0.05 and then minus 6.5 divided by 0.05. So that's VA, which you can calculate directly. This K is equal to 9 times 10 to the power of 9, and then I'm going to multiply 1 times 10 to the power of minus 9 for the nanocoulomb, and then I have this to add. Yeah. Okay, so that's VA. VA. VB, so this is V at point B. Again, it will be 9 times 10 to the power of 9, and 1 times 10 to the power of minus 9, and then I have what? 2.4 divided by 0.08 minus 6.5 divided by 0.06. Okay, so I got VA and I got VB, which are numbers now, in volts. Okay. So I got that, and then he said, find the work done by the electric field in taking a charge that is equal to 2.5 nanocoulombs from point B to A. How do you do that? How?
Q1, Q2.
You don't need to do that. But, okay, what did we say about the definition of V? Is equal to what? Over Q naught. Right? So if I want Q, which is the change in work, remember he told me that from infinity. So this will be minus it, right? So all I have to do is what? Is equal to Q multiplied by V. That's it. And in this case, it's V, he's going from what? From VA to B. So VA minus VB. That will give you the work, and that's it. Okay, so you don't have to do that work when you Q to over R and all that business. Okay? Another question, all of these questions, by the way, are from the end of the chapter. Okay, so what is this? It says that a proton moves a distance 0.5 meters in a straight line from point A to point B. So I have a positive charge that is moving from point A to point B. Okay, which is distance between them is 0.5 meters. So this is 0.5 meter. Right? And the electric field along this line is equal to that much. So electric field E is equal to 1.5 times 10 to the power times 10 to the power of 7 volt per meter. Okay? And what does he want? Determine the force on this proton. What's the force of this proton? Very quickly, guys.
The force equal to Q times E.
F is equal to QE. Right? Q is the charge of the proton, which we know 1.6 times 10 to the power minus 19, and the electric field is 1.5 times 10 to the power of 7. I want to ask you a question. This is the unit that I've used now for the electric field.
We need to convert it.
Is that the same unit as we are used to? What's the unit that we use for the electric field? Newton per Coulomb. Now, as homework, let's see if this is equivalent to volt per meter. They are? Okay. So, we'll do it next time. Okay? Sorry? That's an hour? Okay, that's it. All right? So, anyway, so we got the electrostatic force, determine the electrostatic force, and now he wants the work done. Physics 1. The work done. What's the work defined as? Work is equal to G cosine theta. That's the definition, the fundamental definition. Yeah, if you have it, right? If in this case was that one. D is the distance, he told me 0.5, and he said they are along the field. So that means the angle is theta is equal to 0 degrees. And then you can calculate that. Guys, the questions on chapter 23 are very straightforward. You just have to make sure you understand that slide that I started with the beginning, the definition of the electrostatic energy, potential energy, and the definition of the electric potential, the relation between them, problem solved. Okay. So make sure that this is something that you should not make any. I was happy that they included 23 in the midterm. Okay, so let me just very quickly go over this, just so that we set it up for next class. And then we'll be done with chapter 23, and we finish all the material related to. So, guys, please. Now, by definition, and you know this, by definition, the work in going from point A to point B is simply FDL, or QFD, right? And if we're going through over a distance, you can't integrate over the distance. If the force is constant, then it's just simply FDL. If I substitute for F with the electrostatic force, and Q is positive, so then it will become, I can do that simply, Q will come out, and then I have W over Q, which we know that is simply VA minus VB, right? The voltage difference. And that is defined as, EDL or E cosine theta DL. So let me write it over here. So the potential difference, delta V, the potential difference is defined as, and going from point A to point B, E DL or E, actually just write EDL. Okay? So this is called the integral form of delta V, the potential difference. Okay, remember, guys, for a charge to go from a point A to point B in an electric field,
Its potential.
the voltage or the potential must be different. So there is no way the particle is going to go to somewhere where the potential is the same. Any particle, if we want to move it across, the potential must be different. So it must have delta V. Okay? So the integral form of delta V, the potential difference. But I can have another definition, because if you remember, V was defined as K, Q, over R, right? This is what? This is the potential due to a point charge. Okay, what if this charge is somehow distributed just like uniformly over some volume or some distance or something? Then all I have to do is just take a small portion of it, and I call it dq. And then I find, first of all, delta V is equal to K dq over R. And if I integrate both sides,
The sum.
what do I get? I get V is equal to K delta Q dq over R. Yeah. So these two formula, this formula here and this formula here, are both the integral form of delta V, or the potential difference. So if I want to calculate the potential difference, I can find it using, if I know the electric field, or if I know the discharge distribution of Q. And this is what we'll do next time, is to look at the calculation of the potential due to some uniform charge distribution or continuous charge distribution that has either a uniform volume charge density, or a uniform surface charge density, or uniform linear charge density. Okay? So I come back to that. But remember what we've taken here. Do I have the summary? Let's go back to the, before we, this is it. Okay? So this is the summary slide, please. This is a very important summary slide of all of chapter 23. All I need to know, there are two things or two quantities that I should be familiar with. One is the electrostatic potential energy. It's the energy due to the movement or the of two charges when they're close to each other. Okay, that is defined by that formula there. From there, we define the voltage or the potential, which is simply U divided by Q naught. So it's basically the potential or the electrostatic energy felt by that test charge when I place it within the electric field. And then from there, of course, in both of these guys, we have algebraic addition if we have more than one charge. And then last, which is the potential due to some continuous charge distribution. Okay? So I'll stop here for today, and we'll do our quiz, and then we'll continue the discussion next time. Can you just spread out very quickly?